everybody. Good morning. We are going to be talking about solubility today. So this is going to be a change in what we have been talking about. Up to this point, we've been talking about heat in solutions. We've been talking about how much heat. Now we're going to start talking about, well, exactly how do we make a solution and what are the parts of a solution? So our focus is going to be on solubility, and basically it can be defined as the ability of a solid, we're going to call it the solute, to be dissolved in a liquid, and we call that the solvent. Or if we have two liquids, the ability of one liquid, the solute, the one we have less of, to mix with another liquid, the solvent, the one we have more of. At any time during this recording, if you would like to stop and take some notes, please do so. These should be being recorded in your notebook. So here we go, everybody. Okay, so what is solubility? Specifically speaking, solubility is the amount of solid solute that can be dissolved in a given quantity of liquid solute, or solvent, excuse me, at a given temperature. So we're going to describe solubility at certain temperatures because solubility changes at different temperatures. So how is it expressed? Usually you'll see it expressed as the grams of the solute in the grams of the solvent, in this case water, at a certain temperature. So it will be always in degrees Celsius. I know at this point we have been talking about gases in Kelvin. Since we will not be talking about gases at this time, we are simply going to be just keeping our temperatures in Celsius. So you will not have to do a Celsius to Kelvin conversion. Okay. So then we have to start talking about, well, what kinds of solutions can we have? And so we have some different types of solutions. And for right now, what I would suggest is that you record these definitions. And so we're going to do, on the very next slide, we're going to do some explanation of them. But just to say, a saturated solution is when no more solute can be dissolved into a solvent at a given temperature. That means some of the solid is just going to rest at the bottom. An unsaturated solution, this means that we have less dissolved than could be dissolved to make a saturated solution. So that means more could still be dissolved. So there should be no solids sitting at the bottom of your container. Finally, a supersaturated solution, this is something that a solution contains more dissolved solute than a saturated solution can dissolve. So we have to do some special things to this. Usually this involves heating it up, putting in more solids, and then allowing it to cool back down carefully so that you can have more dissolved than should be able to be dissolved at that temperature. Okay. We're going to take a look at the graphs of these so you can see what we mean by on the line, under the line, and above the line. So first we have, here is a graph of the solubility of potassium chloride at 10 different temperatures. So from 0 to 100 degrees Celsius. Okay? If we are going to describe a solution of potassium chloride, we would describe a saturated solution as one that is the amount of grams at a certain temperature occurs right along that line, right on the line. Okay? That's called a saturated solution. If we have a special solution called a supersaturated solution, that means that more has been dissolved than was dissolved on that line, and that's because we've done special things to it in heating it up and cooling it back down again and allowing things to remain in the solution without, the terminology is without precipitating out. In other words, without becoming a solid and that solid sinking to the bottom of your container. All right. Then we have the unsaturated solution. And I'm going to move my back, and I'm going to move this down so you can see the definition. The unsaturated solution are solutions that are below the line. They are always called unsaturated solutions because this means that we don't have a saturated solution yet. We still need to add more solid to make a saturated solution. So everything is dissolved and more could still be dissolved. Okay. Now we are ready to move on to our solubility curve. And I'm going to move my picture here. So when we're making a solubility curve, which is what you're going to be doing for your activity this week, we are going to be changing. We're going to play with the amount of water. We're going to play with the amount with the temperature. And so when we make a solubility curve, this is going to be basically comparing the amount of grams of solute to the temperature. But what about if we change the amount of water? What happens then? At this point in time, you're going to want to stop and answer that question. What if we change the amount of water? Think about this. What if we double the amount of water? What does that mean for the amount of solute that can dissolve? What if we half the amount of water? What does that mean for the amount of solute that can dissolve? So let's take a look at that. If we make 1 pack of Kool-Aid, we need 2 quarts of water to do it. If we make 2 packs, if we have 2 packs of Kool-Aid and we want to have the same concentration as 1 pack of Kool-Aid, how much water will we need? Well, we are doubling the amount of Kool-Aid that we want to dissolve, so we will probably need to double the amount of water. So would you expect that our quarts of water would change from 2 quarts to 1 or from 2 quarts to 4 quarts? Okay, so if you said 2 quarts to 4 quarts, you would be right. Okay, so when you're making the solubility curve, in order to reach saturation, if we double the amount of water, then we would need to double the amount of solute. So 20 grams dissolved in 100 grams of water at 25 degrees Celsius means that we would need 40 grams to be dissolved if we have 200 grams of water. That should make sense to you. And it's going to be a basis of us thinking about how exactly we should solve some of our problems for this week. Okay, and I gotta move this up. What if we don't have enough solute? What about that? All right, so what about in order to reach saturation, if we do not have enough solute, we've got to add more. For example, if the solubility is 30 grams in 100 grams of water at 50, and we only have 25 grams dissolved, then obviously we need to add 5 more grams to reach saturation. So we must always pay attention to how much do we actually have dissolved and how much can be dissolved. So in this case, we actually had 25 grams dissolved, but we could have dissolved 30 grams, so we needed 5 more grams. Okay. Now, what about all this dissolving? Why do we care about all this dissolving? Okay, so when we are looking at this, it's going to be what are we dissolving in? And it turns out that what we are dissolving in is water. Water is considered the universal solvent. Why is it universal? Well, let's talk about water a little bit. When we are talking about water, we're going to pay attention to what's water molecule's shape, and as a result, what is its Lewis diagram? You might notice that this is not only a picture of a water molecule, but this also makes up a Lewis diagram. So when we are talking about the water molecule, we're talking about a molecule that forms a V shape. Here's our V shape. It's upside down. And the 2 hydrogens making it up kind of look like little legs. Or if you turned it the other way around, this would look like a Mickey Mouse shape. Okay, one end of the molecule is slightly positive. Sorry, the hydrogens are the slightly positive end. And one end of the molecule is more negative. The oxygen is more negative. Okay, this is creating a polar molecule. So if I were to point all those things out, the oxygen is our negative portion, and the hydrogens are each our positive portions. And I'm going to draw those in so you can see, aha, negative and positive. So we do have a molecule that has an uneven distribution of charge. This makes our molecule polar. And that is really, really important because by being polar, this can dissolve so many more things. It can dissolve things that are polar that are still covalent. It can dissolve things that are ionic because ionic is extremely polar. So water can dissolve many things as long as they have have polar characteristics just like water. Okay, we're going to go on to our next slide. Remember, at any time, if you need to pause, then please do and write down what you have. I think this very last bullet point down here is the one that you're going to want to write down. Okay, so interestingly, when water starts to freeze, it freezes by attracting the positive side of water to the negative side of water. So you'll notice that the oxygen and the hydrogen start to attract each other. Here's our oxygen negative, and here's our hydrogen positive. And when they do that, water makes a hexagonal shape. And that hexagonal pattern causes water to expand its volume when it freezes, and that is what causes water to be less dense. In other words, that's why your ice floats. It becomes more buoyant. So if you're writing notes on this part, talk about water's hexagonal pattern, and then talking about its less dense and thus the reason why it floats. Okay, we're going to move ourselves along. All right. So what about these physical properties of water? You know water is transparent. It doesn't have an odor. It's almost colorless. It is not pure if it has things in it like minerals or other liquids or gases. It would look different. It would taste different. It would smell different. Okay. Water has this hydrogen bonding. In other words, hydrogen is attracted to the oxygen, and we are going to that's going to be the reason why water has some of its properties. Interestingly, this idea that a lizard could walk on water is one of the properties we're going to take into account, because water, as a result of hydrogen bonding, has surface tension. So let's take a look at what is actually happening there. So I'm going to press play on this movie, and we are going to take a look at what it looks like, and I'm going to try to narrate as we go along. So this is about the basilisk lizard. Well, I thought I was. Let's see here. Can I make that happen? Maybe I can't. Okay, too bad. Let's go ahead and move ourselves along then to, well, there it is. All right, so here is our lizard, and I'm going to, he lives in the Amazon, and when he runs across the water, he takes into account many things. So I'm going to all right. So there is our lizard, and he's checking out that dragonfly. And while he's checking out that dragonfly, he's going to want to chase it. And he is a carnivore. He's trying to eat what he can. So if you watch him, once he gets in the water, he's using his tail as a counterbalance, and he's using his feet as a way to make sure that he stays on top of the water. The water has surface tension so that it keeps the lizard up, and he's able to use a lot of surface area on his feet to hold himself up. The other thing that he has is he has to move fast. As you can see, if he were to slow down, he would sink. And this is why we can't do this. People can't walk on water because we do not have surface area on our feet, and we cannot move that fast, not as fast as this lizard can move for his body weight. As you can see, that's kind of amazing. So he's called the Jesus lizard because he can walk on water. Okay, we're going to move ourselves along here. So when dissolving occurs, you can see the little video going on here. When dissolving occurs, we dissolve from the outside of the compound to the inside of the compound. So the particles on the outside dissolve first, and then the particles on the inside dissolve in layers, layer after layer. So the final thing we want to do is pay attention to this. I have highlighted the things that you want to pay attention to of how can we affect the dissolving rate. And this, I would stop this right here if I were you and make sure you get this entire table completed. Okay, that is all you need, everybody. Bye-bye.